Okay, so I'm gonna, have I started recording? Yes, I have. I'm just gonna assume that we're still on speaking terms, so that'll be easier. Good morning, everybody. I'm glad to be speaking to you. I'll show my face real quick. There I am. I am going to do the following for this lecture. I'm going to try to show you just a very brief overview, and then I'll take questions, and I'll get some feedback and ideas. But first off, just to maybe just get us all on the same page, I have had quite a few people asking me questions in the last few days. So I have a fairly good idea of what's not working out or what you're not getting. So let's just look at that to start off with. Firstly, there seems to be quite a bit of unclearness or not clarity with regards to how this whole thing is supposed to work. So just in very broad terms, you're making a transmitter, you're making a receiver. This transmitter has a pull-up, or at least the line has a pull-up resistor, which keeps this high. And then on this side, you obviously have data in, you have a clock, and in this project, I made it easier, and I said that you can use the same clock on both sides. So it's called a synchronous. Oh, why has my screen just disappeared? I don't know, actually. Let me just see what's going on here. Sorry. I'm going to assume that you also lost my screen. Let's just see who comes back. Please come back. There you go, something's happening. There we go. So in this one, the clocks are connected. So it's a synchronous serial receiver. In the real world, you probably have two separate clocks. The receiving clock will be much faster so that you can do asynchronous receiving. The only other thing that these two share is actually the serial line. So for this transmitter, the whole transmission is initiated with start TX. For the receiver, the whole thing is initiated by a fall in that serial line. So if this serial line goes low, that says everything's supposed to start now. So just in terms of the state machines, you need to draw a state machine for each one of them. And hopefully you've all, well, I know you haven't, but most of you have watched the state machine lectures. So in terms of the state machine, both of these will just have an idle state. And in this idle state, it's just waiting for something. Nothing's happening, idle. Actually, let me make it a bit bigger so that I can show you what the outputs are as well. So there's an idle state and an idle state. And this is the state into which this whole thing will go into when the power is reset. What you need to do is follow a structured approach to solving this problem. And the structured approach is very nicely highlighted with very small steps in, I don't know why my screen is going off, actually. I can see on my other screen it's going off all the time. So I'm just going to jump off my one device and just get onto the one. Sorry. Can anybody just confirm that you can still see my screen, please?
Yes, you can.
Okay, brilliant. Thank you. So yes, so what you need to do is then design this through the very structured approach where you type in for each one, or at least you go through each one of those steps. And the first and fundamentally most important step is obviously to understand the problem. So understanding the problem may have been a problem for some of you, but I think I've given enough tips to at least make the transmitter easy enough. So for the transmitter, I've told you there's an idle state, and then it goes into another state. This is clear enough when start TX goes high. So there's some other state. Now you can call the state whatever you want. I called it transmitting. And this transmitting state is a state in which bits are passed onto the serial line one by one as they're shifted through a shift register. Now you could have done crazy stuff. You could have said, I want one state per bit, but that really complicates it substantially because then you have to have many bits to represent the state machine. So in this case, my state machine has an idle and a transmitting state, and I've decided that when it's done transmitting, it's going back into the idle state. Like I said, you could have done idle, transmit bit 1, transmit bit 2, transmit bit 3, etc. But that's just crazy. You're going to end up with too many states. Easiest thing to do is just go into a transmitting state and an idle state. And then the question is, what drives the transition in this state machine? So this transition here is obvious. That is start tx is equal to 1. What drives this transition? That should also be obvious. If it's not, just think about it carefully. The start transmit says start to push my data bits and my parity bit and my stop bit onto the serial line, which means it needs to transmit, it needs to keep transmitting for a start bit, 4 data bits, a parity bit, and a stop bit. So it needs to stop doing this when there's a certain count that equals a certain amount. Now your first guess may be that this must be 7. It's not quite, but it's close. I'll tell you why in a second. So this is the first step. You have 2 states. They have transitions. The transitions are caused by certain inputs, which means in terms of our state machine, if you think about the state machine, we have 2 states, which means we just need 2 bits to give numbers to the states. State is equal to 0, state is equal to 1. So all you need is really one flip-flop with which to represent the state. It's just one single flip-flop, which is going to represent the state. So what we need to calculate is the inputs into the next state and then the output logic. So it's input logic, which is really, oh, sorry, I'm calling it input logic. That's not correct. The next state logic and our output logic. This is the 2 things that we need to then determine. Now, in order to determine, you need to figure out what are the inputs. So the input into our state machine should also be clear from the state diagram. And just check here. So the first input is start tx. That's an input. And the count reaches a maximum. Now, you may ask yourself, what count? Where does this count come from? You're just going to implement a counter. So you're going to basically use a counter from digital. So in digital, there's a component called counter, and that'll provide the count to you. So the inputs here are really simple. I'm just going to take this out. So this is start tx, and this is count is equal to some value. So let's actually give it a nice name. Let's call it count max or count Dracula. Count max. So we need to figure out what this logic looks like. And obviously, you should also know that from state machines, the next state is also determined by the present state or the current state. So those are the 3 inputs into your logic, into the logic, next state logic. It gives 1 output, it has 3 inputs, and all you have to do is draw up a Quano map for that. I'll give you a bit more information in a second. And then we also have to look at the outputs. So what are the outputs? In terms of the outputs, let's just think about this. For your output, in idle state, we don't want the counter to count. So I guess one way to do that would be to say count enable is equal to 0. What else do we want to do? We also, in the idle state, we want the tri-state. I'm just going to make it tri-state equal to Z. Hopefully you understand how to make a tri-state equal to Z at this point. And then the other thing is we don't want the shifter to shift. So I'm not giving the actual values here because I don't want to give the answer away. But shifter is equal to off. Okay. In the transmitting state, we obviously want the counter to count. So counter is equal to on. We want the shifter to shift the values out onto the serial line. So shift is equal to on. and we want our tri-state to actually drive onto the serial line. We don't want this pull-up to be keeping it high. We want whatever we want to put onto the serial, we want it to appear there. So we want the tri-state to be equal to on. And that is the whole state machine. So all you have to do now is to take this and calculate the logic here. So given the present state, what are the outputs? And you can see the outputs are basically counter, shifter, tri-state. Those are the three outputs, and they relate in some way to that singular bit there. Hopefully you can just read that off the state diagram. If you can't, then you may want to draw a corner map for it. For the next state logic, you just have to do a corner map as well. So I'm just going to do the corner map for the next state here. This is for the transmitter, everything, nothing for the receiver yet. And for that, you're just going to say, I have two inputs. I have the start TX, I have the counter max, and I have my state in its present state. What is the output? The output is just what is the next state. Sorry, this is supposed to be state, and this is next state. There we go. And for this, you just do a regular corner map. So what I typically tell you to do is to write this down so that the state is the first variable you do. So state, and then start TX and count max. And this is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, etc. all the way down. And all you now have to do is you decide if it is in state 0 and start TX is equal to 0 and count max is equal to 0, what should the next state be? So you can read this off here. If start TX is 0, then the next state should just be equal to 0. If start TX is 0, next state 0. If start TX is 1, next state 1. If start TX is 1, next state 1. So you can immediately see that what's happening here is this is actually a don't care condition, and this is also a don't care condition, because this transition does not depend on the counter. It just depends on start TX. And the same for this state here. You will see that in this state, the transition happens based on count TX, which means it doesn't even worry about the start TX. So this will be a don't care and don't care. So as soon as you've written down all these states or all these conditions, you can then populate this. And truth be told, this is maybe much simpler than you anticipate. Just going to count real quick. Over here is literally one OR gate, two AND gates, and then a few inverters. That's all there is to it. One OR gate, two AND gates. The only thing that I've not drawn here is the counter. And for the counter, you don't have to design your own counter. You're just going to digital into components. Let me just see where it is real quick. It's under memory. So components, memory, counter. And you just use one of those counters. And this counter has an enable. I'm just going to click on it. Sorry, you can't see what I'm doing. I just want to real quick. It has an enable. It has a clear. It has an output. And you can set how many bits this output is. And it has an overflow. So the question then is, at what point do you want this to go high, this input here? And you can obviously put some logic here on the output of the gate of the counter to say, when I've reached 6 or when I've reached 7 or when I've reached 8, I want this output to go high to tell the state machine I've reached the maximum count. You don't have to use the overflow. So some of you have used this overflow. You don't have to. Just check for the number you want to find for. Sorry, I've said this is the only thing I've not shown. The other thing that I've not clearly shown here is there's obviously a shift register as well. And this shift register sits here. It shifts all the values onto the serial line. And it's either loading or it's shifting. And this is the shifting and loading that you're controlling with this shift register on or off. Okay, so now I'm going to start I'm going to stop sharing my screen. And I'm going to try to take some questions on the transmitter. Oh, you guys can't even see my screen, can you? You can. Okay, are there any questions with regards to the transmitter? let's see if I have any hands raised or anything. I'm just going to rejoin the meeting. If you don't, give me a second. Right, Mr. Kulela, or Miss Kulela, sorry, Miss Kulela, what is your question?
Can you hear me?
Yes, I can.
I would 0, but my counter has not reached my max value.
Gotcha. So, Ms. Kulela, that is an excellent question. Thank you. I'm assuming that you can hear my response. Just tell me if you can't, and you can lower your hand if you. Okay, thank you. Okay, so no, don't worry about it. So the short answer is that part of the instruction is just to ensure that you use a state machine. If it was so that you could keep start TX high for the whole duration of the transmission, then you would not have needed a state machine. You don't need memory then. The operator of start TX is the memory. But in this case, I wanted you, sorry, I'm just going to activate my camera so I can kind of look at you while I speak. In this case, I wanted the states to, sorry, I'm just going to switch.
I can't hear you.
Okay, cool. So what I wanted you to do was to say, okay, there's a trigger. There's something that causes the state machine to go into motion. And this is what the state machine does. The state machine gives you the capability to go into a state of doing something based on a trigger and then keep on doing stuff regardless of what that trigger was. So I just showed you let me just actually show that to you again. Share screen. I just showed you the state machine on the transmitter. And what you should see as soon as my screen comes on, there we go. What you should see is this state machine keeps in this state and it does not transition at all, regardless of what this start TX does. So start TX can go to 0. Once it starts transmitting, it'll be in this state. It'll stay here. The only way for it to exit this state is actually if count goes to a maximum. So this start TX initiates the whole thing, but then it remains in that state and it doesn't need start TX to keep in that state. And this logic that we drive here, this logic here will cause that, because we're saying if we're in state 1, if we're in the state, we don't care what start TX is. Start TX is a don't care and a don't care. All we care about is what is count max's state to make that transition. I don't know if that answers your question, Miss. Is it? Sorry, I forgot your surname, Kulela. Does that answer your question, Miss Kulela?
I think
you can
so,
be honest,
because in my state, pardon?
I know you can be honest. Just tell me if you don't get it. Yes?
Yeah, the thing is, in my state diagram, I didn't include the condition for the state diagram, so I don't know if it will solve my question when I go back to it.
Okay.
So already,
okay, but
I'm saying that first I need to go through the state diagram before
yes,
I can.
yes. So let me phrase the question differently. Can you see that the way that I've done it here in my very structured and systematic approach will solve that problem?
Yes, because once you find out the actual function from your state diagram, it will automatically take into account the conditions of the state, the tri-state.
Yes, and that's really the part where I want all of you to go, I've got it. I now understand. This whole structured approach of doing it negates all the questions and all the problems that I may have, because it takes the structured approach. I can't see who else's name is up. I don't know, for some reason. There we go. It says 1 of 70 people. There's someone's hand up. If your hand is up, please go ahead. I can't see who it is.
It's my hand, sir. Can you hear me?
Yes, Ms. Foster. Please go ahead and lower your hand.
Okay, thank you. So I was building the counter on my own, but you said we can use the counter that's in digital. I don't understand how the one in digital works yet. I know you explained it now quickly, but I'm not sure what the clear and the out gives for it to like reset to 7. Or I know if you make it a 3-bit counter, it will count to 7. But how do you make it? I don't know, like how does the counter work on digital?
You've got about 3 questions in that first one.
Sorry.
That's okay. So
I can actually answer that counter thing, if you would allow me.
Please go ahead. I don't know who's speaking.
Heinrich.
Please go ahead, Heinrich.
Essentially, in digital, you need to take the counter, and then you need another component named as a splitter or merger, and there you can just tell the splitter to say how many input bits it will have, like 1 input bit, and how many output bits, say like 3, and it'll give out like the binary code of the counter.
Thank you.
Then you can use that splitter and attach it to an AND gate and connect that AND gate to the clear. As soon as it reaches a certain amount of counts, it'll then clear itself and stop.
Exactly. Thank you, Heinrich. So Ms. Foster, there's actually a video on this on the Teams files. I'm pretty sure I recorded something like this for a student. Maybe someone can just confirm in the chat box. But this is the counter, and what you have to do is select the number of bits. So I right-click, select the number of bits. So if you want to count to 7, you need 3 bits. Now the thing that comes out here is 3 bits. That's a 3-bit bus now because you've selected this to be 3 bits. Then this here is called, like Heinrich said, it's a component, a splitter or merger component, I think it's called. It's under wires, and it's called splitter merger. So if you choose that one, it comes out like this. Now you have to decide what's the input side. So I just told you we're going to go from 3 bits. What is the output splitting? You can do 1, 1, 1, etc. And actually like that, sorry. So this will then give you a splitter that splits up this into that. Now, if you go and look at the semester test final question, I give a very clear explanation, well, at least in my humble opinion, a very clear explanation of how to reset the counter and count to a certain value. So if you want this whole thing to stop at 6, you need to put some logic gates here, like an AND gate, for example. You can put in here to make this stop. If you want to make it stop at 6, this is all you have to do. You check for the condition. Oh, sorry, that's 5, 101. If you wanted to stop at 6, then you just connect those two. It's checking for 110. Or if you want to check for another condition, like, I don't know, 3, you can do this. And then in digital, you can also select the number of bits for the AND gate. So just right-click the AND gate, and you can say, I have 3 inputs. So then suddenly you can connect all to 1. So this will check for the condition 7. But this counter automatically overflows at 7. But you can then check for 7 and make it clear. So stop counting at 7. And this is the enable that I hinted at earlier. And this is obviously the clock. Ms. Foster, between the 2 answers that you got now, have you managed to sort out your question?
Oh, yes. Thank you so much. That's
excellent. Thank you, Heinrich.
Thank you.
There was another question. Let me just try to check who that was. Oh, it was Oyodan or some synonym like that. Sorry, I forgot it now. Please go ahead.
Yes, I have just a couple of questions. Actually, while you're here, I just want to confirm that we are allowed to use more than 2 input gates in the project, because I made use of it, but I wasn't sure whether that's like allowed.
Yeah, of course. Please go ahead, do. That's not a problem at all.
Okay, and then for the actual report part for our results, under the section that says test results, I know that you answered a question on Teams to me actually about it, that we basically need to take two numbers or 2 inputs and then show that our transmitter or receiver or system actually works based on the output that we get from digital. Is it as simple as just like executing our file and then looking at the little diagrams that come up for the clock in terms of time and the inputs for the buttons and the outputs that our transmitter on the serial line is producing.
Yeah, so I was hoping that what you would do is to, let me just see if I can get it going here without showing you the answer. So I was hoping that you would show me in this type of form the serial line for 5, for example. If you transmit 5, you have a start bit, you have 1010, and then a parity bit and everything. Just give me 1 second. I've got some noise in the background here. Okay, cool. So I was hoping that you would give me the number from the input into the output, and that you would show me the serial line that demonstrates how that is transmitted. And then you had another question, but I think the answer is yes. You're more than welcome to use multiple input AND gates and OR gates. Mr. Knipe asked whether we can use a counter with a preset. By all means, do. There's a nice video about the counter on Teams project channel. Thank you, Ms. Ackerman. Sir made a really good video of the counter in the chat. Miss Kulela, thank you. How will our transmitter and serial be marked? This is a difficult one. So because of your very, very, very low marks for A1, we're kind of trying to keep that flexible. We will probably look at what you've done and see whether you've convinced the reader. I always tell this to the students, just convince the reader. Ask yourself, what do you need to see to be convinced that it works? So put that in and we will mark it accordingly. We'll run the tests, we will run on digital, and then we'll use some of those tests that I've given you to check whether the system actually works, and then we'll mark the report separately based on a rubric. What exactly should we include in the report? So convince the reader and try to capture the proof that this thing works. Okay, more questions? I don't see any hands. So the design part is mostly marked based on the result of your test. So we're marking your circuit, we're marking based on the tests. So we're actually using digital to mark it with command line instructions, and then we are we're marking the report separately. Yes, Mr. De Beer, please go ahead.
So does this mean if a test is completely successful, as in my transmission test is successful with everything, do I get full marks there, or will there also be looked at how our circuit is built to?
Okay, that's a good question. Yes. So the only thing that they will check in the that they'll run the tests, and there may be one extra check that's added, and that one extra check has to do with the parity bit, but we won't check your circuits in digital except to check that there's no link between the transmitter and the receiver. So if, for example, if you use start TX in the receiver, then you've basically cheated the system. So we'll just check that the only link between transmitter and receive is the serial line and obviously the clock. And apart from that, we won't check your circuit in digital. Then we'll check your reports where you will probably paste your circuit diagram so that we can mark the report. I guess that's what you asked, Andre?
Yes, that's
brilliant. Thank you.
No, actually, if it mattered how many logic gates we used, if we needed to use the amount.
No, you can go crazy. You can go to town. You can use every single logic gate that there is in digital.
Okay.
Is there a template that you'd like us to follow? I wanted to have a template, but in the end we decided to leave it out, just to give you a bit more flexibility, and it also gives us a bit more freedom in the marking, Mr. Bester. So we'll be looking for, have you captured the design, and have you proven that you know what you did? Have you described what you wanted to do? So it's the report is really just there to not just give you a binary mark. Otherwise, it was just a yes or a no for each test. So it's just a way to give us some level of flexibility with the marks. Mr. Bester says, thank you. You're welcome. Will we have to implement a check on the parity bit to confirm that the bits transmitted are correct? Ms. Prinsloo, thank you for the question. So you have to give out just what the received parity bit was. We didn't want you to do the parity error check necessarily because it complicates matters significantly if we have to introduce a parity error on the line. So you just have to tell us what parity bit you received. So we're checking the parity basically in the transceiver side, sorry, the transmitter side. Mr. Udayan, please go ahead.
Hi, sir. Just another question while we're on the parity bit checker. I think it said somewhere in the project brief that if we do implement a checker or some sort of system like that, then we need to just document it separately within the report. In terms of page limits, because 5 is becoming a bit too restricting, especially when we put in circuit diagrams and stuff like that in. Will that need to still form part of the 5 pages, or is there some flexibility with that? And will we be penalized if we go over it?
Yeah. So please don't go over 5. Stay to 5 pages. They will only mark the first 5 pages. If you're concerned that you have more information that you desperately want to share, just dump it into the appendix. But we're going to mark the first 5 pages. And the gist of what we want to get is, did you do your own design? Do you understand what you've done? So you really don't have to go to town on this report. It's just, like I say, it's to give us a bit of flexibility in the marking, so it's not just a yes or no, a pass or fail. Okay.
Okay, thank you, sir.
Sure, you're welcome. There's another hand, but unfortunately I can't see who it is.
Hello, sir. Can you hear me?
Yes, I can.
So, yes, sir. With regards to the parity check, you say we don't have to have a parity error check or something like that, but surely that 1 or 0 you're going to get in the parity is going to be based on the even or odd of the parity.
Exactly. So yes, you're absolutely right. So if you wanted to check it, you can just check that. What I'm saying is, in order for us to fully check the functionality of the whole system, we would have to check for false positives. So we would have to insert an error, do a fault insertion testing, and that just complicates matters, because I think most of your peers will agree that it's already complicated enough.
Yes, sir. Then, so let's just say that you do get your parity is wrong. Let's just say for whatever reason your parity is wrong. Do you have to have any consequence of that, or do you just say in your report that parity was wrong for whatever reason? Or must you redo the test or something like that?
No, if parity doesn't work, you're just going to lose a few marks. So basically, if your transmitter works 100%, and you properly document it, you will get at least 50% for the project. That's how it's been developed. That's how it's made. So if you, I don't know how many marks we're going to assign to parity, but I'm guessing it'll be probably like, I'm guessing here, so don't hold me to it, but I'm guessing you will get, let's say the project comes out of 100, you will get 50% for the transmitter, and you'll probably get 40% if your parity doesn't work. But just help me, Mr. Potgieter. The parity is not rocket science. Why don't you get the parity?
No. So I completely understand it. I'm just saying, for whatever reason, if it weren't to work, what is the next step? But it's obviously just to fix and make sure it works. So no,
it must work. Yeah. It's
no.
Not a challenge. Yes.
I just saw in some videos they said if the parity doesn't work for whatever reason, you must repeat the transmission or something like that. So I was just wondering.
Is this from internet sources?
Yeah, this is just a random YouTube thing I found.
So the idea there is, within a second, Mr. Chawatama, the idea there is just the parity bit is there to indicate or to help identify if there was a transmission error. So if there was a transmission error, if there's a parity error on the receiver side, then the receiver will typically send back to the transmitter and say, not acknowledge. I haven't received the message adequately. Please send it again. But we haven't implemented anything at that level on this project. I just want to show you something real quick. If you can see my screen, I don't know if you can. It seems like my screen is not sharing for some reason.
Yeah, I can't see it at the moment, sir.
Bugger. Okay, sorry. I just wanted to say that the parity bit is literally just an XOR gate. There's nothing funny about it. It's
yeah, no, I've already done it. So I was just in case it didn't work, I just wanted to find out.
Okay, I can see that you're worried. That's partially good, but also not only good. Actually, I'll just show you the parity part because that's so silly and small. And let me just share it with you.
With that, so in the report, do we have to show how we built the parity logic? Do we have to show the checkerboard, corner map, and all the solving and stuff like that?
No. You just need to show what you did. Can you see what I'm showing you now?
Yes, sir.
That's the whole parity. There's nothing to it. It's really as simple as that.
Okay. Okay, cool. Thank you, sir.
The parity it's supposed to be a joke. Okay. No one's laughing though. Okay, so who's next? I see there's another hand on, but I can't see who it is. If your hand is up, please go ahead. Or lower your hand. Oh, it's Mr. Govender. Mr. Govender, your hand is lowered. Yes, go for it.
Hi, sir. How are you?
I was better until we had A1. And you?
Same.
Go ahead. How can I help you?
So I have two questions. For the buttons in so if you can just open the template quickly, so I can just show you.
Do you want me to open the template?
Yes,
okay.
Please.
I'm going to open version 2. Is that okay?
Okay.
Okay, cool. And I'm sharing screen in a second. Cool. You should be able to see it now.
Okay. Yeah. So with regards to the buttons, will the buttons be, so say if you, for example, if you want to transmit B5, will the buttons be left on, or will it be the same as the start thingy where it can be put on and off, and it must just know that there's been a 5 input?
Do you mean when we do the tests, or do you mean while you develop and check it?
When you do the tests.
So for the tests, you should actually be able to see this. Just look at this real quick, Mr. Governor, and tell me if this answers your question. So this is test 1. I'm right-clicking it, and I'm clicking Edit Detached. This is the test, right? I don't know if you can see that level of detail on my screen, but this says for the first time instance, apply this. So I'm just going to widen this a bit. And if I go down, so you can actually go and look at my test. I've got comments in here to say what's happening when. So you can see the first thing that happens is I'm setting B5 to 1. I'm keeping it high for 3 clock instances. Then I'm setting start TX1 while this 5 is equal to 1, setting it 1 for 3 clock instances or clock samples. And then I'm waiting for this transmit to go through. So that's basically my test. And here's what I'm testing. I'm testing serial output. The last column is what I'm testing. So I'm saying I don't care what it starts out with, but when I say start TX, I'm expecting on that same clock that the output must be 0.
Okay.
On the next clock, output must be 1 to denote D0, etc. Does that answer your question, Mr. Governor?
Yes.
I think many of you may actually have benefited from what I've just said. Hopefully you did.
And another question I have with the parity TX above the stop bit TX, what I'm not understanding. What do we do with that?
Okay. Yeah. Okay, cool. So actually, I had many people with this question. I'm just going to try to start my screen sharing from this side again. Hopefully that works this time. Let me just get on here. Thank you for the question, Mr. Governor. And I'm going to start screen, hopefully from this side. Share screen, start broadcast. Crossing fingers. Something's happening. Yes, success. Okay. So what I want you to take is the following. The parity bit is supposed to tell you whether you're using odd parity or even parity. So parity is a mechanism by which to check if an error was on the line, if there was an error on the line where it was transmitting. So this parity bit that you have, the only thing that it does is it says, is parity odd or is parity even? And the way that parity works, this is maybe very important to understand. It's in lecture, I think it was lecture 9. Parity works in the following way. It's, if we're using even parity, we're adding a bit to the data stream, and that bit is set to 0 or 1 in such a way that the total number of ones is even. So I'm just going to say that graphically, maybe to make it a bit clearer and easier to understand. So we have data bit 3 to data bit 0, and we have a parity bit. This excludes the start bit and stop bit. We don't care about them. The parity bit, if we're working with even parity, then this parity bit is set to 1 or 0 to ensure that the total number of ones is even. So for example, if we're using even parity and we have 1101, then this parity bit will be equal to 0, the transmitted parity bit. So this input parity that we have tells you, are we working with even or odd parity? So if this is 0, we're working with even parity, and then we need to make this 0 to make the total number of ones an even number of ones. If we're working with odd parity, so if this was equal to a 1, then and we had 1100, then this parity bit here would have become 1, because the total number of ones must be an odd number. Just going to do another example to be sure that I capture all the use cases. Let's say we're trying to transmit the number 1110. So now our data stream has 3 ones, and let's say our parity selector or parity mode input is 0. So we're working with even parity. Then this parity bit becomes a 1 to ensure that the total number of ones is an even number. It's 1, 2, 3, 4. If this is set to 1, means we're working with odd parity. That means that this will turn into a 0 because there's already an odd number of data bits. Now, this sounds all complicated and really difficult to implement, but the fact of the matter is an XOR gate does that for you. You don't even have to think about it. So if you listen to the lectures, and I think I've made an extra video on this. I can't remember if it was a recorded explanation or just an explanation with someone. But the parity bit already, sorry, the XOR gate already does that. So if you have D3 all the way to D0 here, and just that parity input, or whatever the parity selector, those 5, if they're XORed, that gives you the parity bit output. This is the parity bit that is transmitted. Parity bit, and this is the parity selector if you want, or the parity input. Mr. Governor, that was much more than you asked, but does that help you? Does that answer your question?
Okay, I see. So the parity bit TX is just you're basically changing modes, if I can put it in that way.
Exactly.
Okay.
Yeah, for lack of a better term, I think this is mode is maybe a better word to use there, but the parity mode if you want. People
Okay.
always just say it's even or odd parity. That's what the input does. So yes.
Okay, cool, perfect. Thank you, sir.
Hopefully some of you found that useful as well. There's another question. Let's just see. I don't know, Miss Prinsley, sorry. Yes, Miss Prinsley.
So I was just wondering about, you said the counter being max isn't 7. If you don't want to, like, I'm not asking for the answer, but just why wouldn't it be 7 if there are 7 bits that are being transmitted?
No, actually, I'm quite happy to explain this to you. I'm really concerned about you buggers, and bugger is a very bad word. Sorry. So the idea is that we have a start bit in our bit. This is my shift register. I have a start bit. I have D0. I have D3. I have D. Just going to redo this. My shift register has a start bit, and it has a D0, D1, D2, etc. D3, and then a parity bit and a stop bit. This is how I implemented my shift register. And obviously in front of each one of these, there's a little multiplexer that selects, am I loading or am I shifting? And that multiplexer is controlled by your state machine. Now, you had a question. Oh yes, why is it 6 not 7? When you enable the, what is this called, tri-state, the tri-state buffer. If you enable this tri-state buffer, as soon as the start TX goes high, so as soon as start TX goes high, the state changes immediately to enable this output, which means that this this 0, the start bit, is immediately on the serial line. It doesn't take an extra clock cycle for it to appear. So I think what I'm trying to say is this start bit doesn't have to shift. It is there. It's just a matter of enabling the output. So this first bit you get for free. It doesn't cost a clock cycle. So all you're left with is D0, D1, D2, D3, the parity bit, and the stop bit. Ms. Prinsloo, does that answer your question?
Yes, sir. Thank you so much. I actually had a problem with that thing, yeah, with my start bits counting. Yeah, perfect. Thanks.
Great, you're welcome. I don't see any more hands. While you guys are thinking about more questions, oh, there's a hand. Mr. Odayan, please go ahead.
Hi, sir. Sorry, I'm back. Just really speaking about the counting to 7 thing and why it shouldn't work. Yeah, I'm basically counting to 7, and it is working. So,
certainly, is it? However, is it working such that the second byte that you receive is also correct, and or the second nibble is also correct, and is it immediately correct?
Okay, so currently it's passing all the tests.
Okay, fair enough. So, Mr. Odayan, I think I'm just going to make a call here and say that's fine. Then don't worry about it. If you're sure that you pass all the tests and everything works, then don't worry. I obviously don't have insight into your design. If you pass all the tests, then don't worry. I'm describing here with the 6 is how I designed it, and if yours works with 7, by all means.
Okay, I think it's the way I implemented the outputs of the counter. I think it was different to the way you wrote it in your initial truth table.
Okay.
I don't know whether that made a difference or not.
It really, there's more ways. There are more ways to skin a cat. It's just the way that I've designed it. I used a very structured approach because I wanted to be sure that you got it. In fact, my first design was totally different because I used a non-structural approach to do it, and that then worked differently. But the outcome was the same. So don't worry about Mr. O'Brien.
Great, thank you, sir.
Cool, Mr. Chawatama, go ahead.
Good morning, sir.
Sorry, you had a question earlier.
No, you answered that question that I had earlier, but this is on what you just said now, when she was asking about the 6 bits. So when the start bit is transmitted, would I be correct to say after 1 clock cycle, since I'm feeding that start bit directly into the tri-state buffer, it would switch off as soon as the next bit comes on? Like, let's say
tri-state buffer the tri-state buffer will stay on, but after the first clock cycle, everything will be shifted through. So, sorry for interrupting you. Go ahead. Sorry. Do you want to finish your question?
You can go ahead, then I'll see if it answers my question. If it doesn't, then I'll carry on.
Okay, cool. That's one of the best offensive tactics of being a lecturer. Just start to answer the question to which you have the answer. Okay, so this is the start bit, and this is D0. So as soon as your state machine, as soon as that state machine clocks through the next state, then this output enable will go high, and the 0 will appear here. That start bit 0 will appear here. However, on the next clock cycle, this D0 will be clocked into this position here. So its meaning isn't start bit anymore. It then contains D0. So this D0 must then be present here. So whatever is D0, this output enable must stay high until all of these bits have been shifted through. So this output enable must stay high until you reach the end of the transmitting state, and it jumps back into the idle state. Does that answer your question, Mr. Chawatama?
Yes, so what I'm saying is for it to remain high, should I not implement something like an SR latch that keeps it high and then resets when the stop bit comes through or something of that sort?
That's exactly what the state machine does. I'm just going to try to zoom in here and hopefully I don't lose you. Yes, it's working. That's exactly what the idea of the state machine is. So this state machine has the tri-state enable low in idle and the tri-state enable high in this transmitting state. So the state machine does that for you. That is exactly, I don't want to give away too much, but that's exactly what this output logic does. This output logic is actually just copper. It's just wire. There's no logic even here. When you're in state 1, the output enable of the tri-state must be equal to 1. So that's done for you. You don't need an SR latch. That's exactly what the flip-flop does for you.
All right, thank you. That answers my question then.
I'm very happy to hear that. Let me just check. I've got a few questions here in the stuffy majig. If in the project document a stop bit error check is mentioned, what exactly is a stop bit error? Oh, that's good. So, Mr. van der Westhuizen, thank you for the question. In the real world, or in the real world, the transmitter and the receiver uses the serial line. There's no way for the receiver to know whether the line is broken. So, if the line is broken here, let's say a kleine Morsi goes and sits on the wire and breaks the wire, then the receiver will receive 0 for a start bit, 0 for the data 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 bit, 0 for the parity bit, and then a 0 for the stop bit. So the stop bit is used to indicate the line is broken. If the stop bit is not 1, for example, in this case, then it says the line is broken, don't trust the data. So it's used for a broken line indicator. What was your question again? Oh yes, so that's a stop bit error. I hope that helps, Mr. van der Westhuizen. Mr. Karstens, am I correct in saying that we do not use the stop bit as we are always sending the same amount of bits? No, we're using the stop bits. The stop bit is the last bit you're sending, and you're always sending it. Maybe I don't understand correctly what the stop bit is used for. Hopefully that makes more sense now. Mr. Karsten, do you want to just frame that as a question? Works with 7 clock rises and yours as well. Well done, Mr. van der Westhuizen. Are we allowed to use a comparator? Ms. Duran, I'm concerned about why you want to use a comparator. But if it floats your boat, why not? Mr. van der Westhuizen says thank you. Mr. Karsten, maybe just come back to me if you have another question on that. Any more questions? Hands? Yes, Ms. Ackerman. Or Ackerman.
Hi, sir. Yes. Do you perhaps have any advice for someone who's managed to build a circuit that passes all the tests without doing the very step-by-step drawing the state transition diagrams or any kind of tables or Conner maps? Because then I almost reverse engineer my thing. Or should I just sort of start from the beginning very systematically and see if I can get to somewhere similar where I am now?
I would say at least do the transmitter very systematically so that you get your marks in the report. Because the issue with it working but not using a state machine in the report is maybe going to be a problem for you. Like I said earlier, it's possible to do this thing in many ways. And the first iteration that I did, I also didn't use a state machine for the transmitter. So I just wanted to get it done real quick because I was in a rush. But we want to teach you how to do this systematically. And I'm 100% sure, Ms. Ackerman, you struggled a lot to get this thing working. And looking at the way that I described here on the screen now, I'm also fairly convinced you must agree this is an easier way to do it. I'll take that as a silent yes.
Yes, okay, thank you, sir.
I would recommend just do it this way. Yeah, I think you'll get away with some of it, but rather do it properly.
Okay.
Someone's in the same boat as her XD. What does XD mean? Is there some strange meaning to XD? With no systematic approach. Mr. van der Westhuizen, but that kind of misses the point. That just means that you're very clever, but you didn't really understand the procedure or the process, which means there's a place for you in this world, but I don't know how much you got for the exam. Maybe you want to play it safe. How do we add new variables like max count to our timing diagram? Oh, that's very simple. In your that's a good question. Sorry, Mr. Visser, thank you for that. Just see. So if you want to add a variable, and you say variable, you mean signal, right? If you want to add a signal to your timing diagram, you just add one of these babies. This is exactly why I have, things are going wrong, sorry. This is exactly why I have that there. You just add one of those, these outputs. I think they're called outputs. Let's just check.
We don't see anything yet.
That's not good. Just give me are you sure? I'm going to take it you are. Sorry, I'm just going to re-share then. Beg your pardon. Stop sharing and start sharing. Just tell me when you can see it, please. Thank you. And you should see it any second. Yeah. I can see it on my other device. I'm going to assume that you can see it. Yeah. Okay. So that this here is called an output terminal. So if you just add one of those and just see where they are, it's just an output. So as soon as you add one of those, right click it and give it a name, then that'll pop up in your simulation as a signal. Hopefully that answers your question. XD is a sideways laughing face, closed eyes, and D as the mouth. Sorry, I only laugh at dad jokes. How do we add new variables like max count? Well, that's what my daughter says. I've already have that. Sorry, Mr. Pfister, does that answer your question? Yes, it does. Great. Ms. Kulela, hi, sir. I just want to make sure that the enabling of the counter is already taken into account in the state diagram, since the counter is one of the outputs. I think you're referring to my drawing that had counter in there. And in fact, that is exactly what I mean when I say counter. It's the counter enable. It's the thing that causes the counter to go yes, count. So that is one of the outputs of my state diagram. Let me just show you what I mean. Oh, wow, swapping between devices is quite a challenge, I must say. So one of these three outputs is actually the thing that's making the counter to go count, and that's if this is tri-state on, shift enable, counter on. Oh, I see. There's a bit of a delay. Tri-state, shift, count. I thought the same. Just wanted to make sure. Okay, cool. Okay, guys, help me help you. Any more questions? I'm going to stop the recording unless you have more questions, and then I just want to make a few observations real quick as well. Yes, there's a hand up. I can't see who it is. Please go ahead.
Yes, sir. I just wanted to find out if there's any, I almost want to say like any tips that you can give us when working with the receiver. Any things that would benefit us, not give it away, but just benefit us when working with the receiver and not necessarily the transmitter.
Yeah, that's a good one. So for the receiver, it's essentially the same design. Who was that? Mr. Claassen. It's essentially the same design. So for the receiver, I'll tell you what I did, and you can do something similar if you wanted. I have an idle state. In this idle state, I'm expecting to receive a low on the serial line. When I receive a low on the serial line, I go into a state where I have receiving. This is the state in which I'm receiving. Then after I've received all the bits, I need to make data ready high. So I have added a state here called data ready high. And then I said it goes back into idle state again. So hopefully what you can see is this transition, sorry, I can't tap my screen. Hopefully you can see here, this transition is just serial is equal to 0. This transition here is when I've received enough bits. Mr. Clausen, you should probably hear from the words that I'm using that that's just a counter. So it counts, have I received all the bits? This here is just making data ready high. So the output of data ready here will be equal to 1. In the other two, it will be equal to 0. And obviously here, my counter will be disabled. That's in the idle state. Why is it not flashing on the screen? There we go. And here, the counter will be enabled. And the shift register will be enabled here. That's in my receiving state. And this transition here will just happen. The output enable will be high for one state, and then it goes into the next idle state. So nothing causes this. It just happens. The clock cycle causes it to transition here. And it disregards all the other inputs. And for this one, it's just a counter. Mr. Clausen, does that help?
Yes, sir. Thank you very much.
I hope I haven't given it away. I don't want to spoil your day. Okay, there's another question.
Hi, sir.
Yes.
So I just wanted to ask, we are transmitting the start bit is high to start transmitting, but the serial line waits for the receiver waits for a low on the line to start receiving. So
Yes.
yeah, should we implement a buffer then on the start TX, or
No,
a little bit?
No. The effect is basically that there's a 1 clock cycle delay between you pressing start TX and the receiver knowing it's receiving. You don't have to do any buffering or anything. It's going to come in. You have a shift register, and as soon as the output enable goes high, the receiver will see there's a low. So on the next clock cycle, it'll shift in because its state machine says you have to shift in.
Okay, perfect. Thank you, sir.
So you don't have to do anything funny. Okay, sure, you're welcome. So the one is triggered by the start, and the other one is triggered by low on serial input. Mr. De Beer,
you need a tri-state buffer for this receiver. Is that correct?
What did you ask, Mr. De Beer?
So we don't need a tri-state buffer for the receiver. Is that correct?
No. It's not driving the line. It's an input. It's actually a flip-flop input on the line, so you don't need any buffering there.
Thank you.
It's just reading. It's never driving. Never writing. I see there's something else going on. Tips on the receiver side, Mr. Lakok, I think you're just a few seconds too late. Oh, sorry, I guess that's why the other person asked for it. And then for the parity bit, after building the parity bit with the XOR gate, how is it connected to the transmitter? I just use a flip-flop in my shift register. So it goes directly into the shift register, into that bit of the shift register. So it's as if you're loading data, it's just you're loading the output of the XOR gate, Mr. George Kayode. Praise. I'm going to stop recording now.